Hey guys, in this video we'll be talking more about the correlation coefficient and the coefficient of determination, or also known as R squared. So the correlation coefficient in your textbook is typically represented by the letter R. Okay, so the letter R is how the correlation coefficient is actually represented in statistics. And the t statistic, which is associated with the correlation coefficient, is given by the R multiplied by the square root of n minus 2 divided by 1 minus R squared. Okay, so let's try and actually do an example. So here we're looking at the age of an individual and the time to finish a half marathon in the number of minutes. So we want to compute the correlation statistic. So we could use the Excel formula correlation, select the first array, and select the second array, and that would give you the correlation. So this correlation is at 0.25, which is not very high. And if you go back to your Excel chart in some sense, well, okay, let's open the textbook again. So if you go back to this picture over here, so 0.25 still suggests that it's a weakly positive correlation. So how confident are you that there's a relationship between the age and the number of how long do they take to actually finish the marathon? So your intuition tells you that there's older people usually should take longer times finish, and younger people should finish the marathon faster. But it doesn't always work that way because there could be selection. Only the fittest, oldest individuals might run a marathon, whereas a lot of the younger individuals, even if you're not very fit, you might still attempt a marathon because you want to become fit. And there's all sorts of selection effects which could occur in who chooses to run a marathon, right? So you're not really sure if this correlation test statistic is significantly different from zero. So in order to figure that out, you could compute your t statistic. So remember from your t statistic formula, so this is R. This is your correlation statistic, which is R. And I don't know why it says that. Underscore there. So that's your R. T statistic, which you can find out, is going to be R into square root of n minus 2. Let's figure out n is 15 observations we have over here. And the t statistic is R multiplied by the square root of n minus 2, the whole thing divided by 1 minus R squared. Square root of 1 minus R squared. And so this t statistic is 0.938. So as you could see, this t statistic is not high enough. It is not greater than the critical value. So this is n minus 2 degrees of freedom. And since the critical value is much higher, you reject this at the, you cannot say that the correlation over here is significant enough. Okay, and for the critical value, you could always go to the t statistic table and you could look at the confidence interval, or since it's a positive value, it's a right tail test if it's far enough from the zero. The degrees of freedom are 13 here, and the degrees of freedom for a single tail at 5% level, one tail test at 5% level, is 1.77. So as our t statistic is less than 1.77, we could conclude that there's this correlation of 0.25 is not significantly different. So this is something which you could always observe. And so that is it for t statistic and correlation, and that's how you compute the significance of a correlation coefficient. And just because, let's say there's another example where the correlation coefficient is much higher, as which you saw in your previous example between height and the number of baskets. So just because the correlation is very here, and you could compute a t statistic over here as well, based on number of observations, and it could very well end up being significantly positive. But just because it is positive and significant does not mean that it's causation, right? So you must have heard this term. If you have not heard this term, so correlation is not equal to causation. So there's a lot of relationships which could happen, which where the relationship is actually spurious. So someone noticed at one point in time, like, hey, a lot of people who eat like ice cream consumption. So ice cream consumption is highly correlated, and with drownings at sea slash lake, So and then someone the correlation, if you're trying to think about it, Scotland, well, you should ban ice creams, right? Stop people from having ice creams because it's clearly having a bad effect, and more people keep drowning at sea or at lake. Right? But this is not the relationship, because we all know ice cream consumption tends to be very high on very hot days. Hot days is more ice cream. And on very hot days, people tend to go to the sea or the lake to have a dip. And the more people who actually swim, the higher the chances of drowning. So this sort of relationship, this high correlation is a spurious correlation, right? It just happens to be by chance. There's no actual theory between ice cream consumption and drownings at sea. So ice cream consuming more ice cream does not make you more susceptible to drown at sea or lake. Consuming alcohol, on the other hand, or smoking weed would definitely cause that. But there's actual theory because you lose impairment and mental impairment when you consume alcohol or are impaired through MJ or marijuana. Whereas there's another example, right? Like from your textbook, the number of the donkey population and the amount of master's degree, right? As the population of donkeys went down in the United States and Canada, the people who are getting master's degree went up in the past many years. Does this have any theory or relationship between them? No, right? Like it has a correlation. They are correlated. They are negatively correlated, but they have no theory. So these sort of relationships are spurious correlationships, and it's very important to know the theory behind the relationship between two variables. In our basketball example, we do have a clear relationship between height and number of baskets. So the next topic which we would be looking at is the idea of R square, which is also known as the coefficient of determination. Okay, and this is known as your R square. This is literally what it is. So R square is just the coefficient of determination, and this R square can be thought of as the explained variation divided by total variation. Okay, so this R square is related to your regression. So let's go back to your example. Yes, so this is your regression of the height and the number of baskets. And in this regression, we did get the coefficient. We got the intercept, and we also got the coefficient on height. So for every inch taller, a person would score 0.38 more baskets in some sense. That's a relationship. So for 1 extra inch in height, the average person who could score more baskets is going to be 0.38. And this relationship is plotted over here. So there are a lot of, it doesn't get a perfect prediction, but this line with the orange dots are the predicted number of baskets, and the others kind of vary around it. So the R square is an idea of how good this line captures the trend in data in some sense. So how much of the number of baskets can be explained by this one variable alone, and that is what the R square tells you. So R square in other ones can be thought of as the summation of y prime minus y bar square by sigma of y minus y bar square. Okay, so Y prime over here is your predicted value. So how much does the predicted value, the variance of the predicted value in some sense, by the variance of the actual value? So that is known as the R squared. This could also be thought of as variance of predicted value by variance of the actual value Y in some sense. So that is your R squared. It tells you how well this regression equation or this variable actually explains it. So here, our R squares for this example is 0.81. That means 81% of the baskets which are being scored of the data can be explained by just this one variable, which is known as height. So this is a very, very, very good predictor. The higher the R squared, typically it just means the predictive power is better. Okay. When you're trying to tell the relationship in terms of a story, R squares are not very important. Like it need not be very, very high. But when you're trying to predict a particular value or predict an outcome, it is the higher the R square, the better it is in some sense. And adjusted R square is another phenomena which just makes a small adjustment to the actual R square, and we will not get into that for now. But let's look at more examples from your textbook. So your textbook, let's go to R square. So this is the coefficient of determination. Let's go to here. We talked about the testing of correlation coefficient. Some exercises on it. So we have the regression equation here, and this distance, the predicted value is over here on the line, and this distance, and every time you have a little bit of distance, the R square tells you how well you could predict it. So the details behind how to actually calculate, once you actually have the formula over here, y prime minus y bar, we did actually calculate a little bit. So the predicted number of baskets are given over here, and the residuals are actually given over here. So you have the predicted number of baskets. This is y prime, and the actual value y can be copied and pasted here. Right? And using this, you could find out your y prime minus y. And similarly, you could also compute your y minus y bar. And once you compute all these values, you could definitely compute your R square. And that will become 0.81. And your textbook gives you more examples. So you have y minus y prime, or y prime minus y, and then you have y prime minus y bar, and like the whole y prime minus y bar square. And once you have the whole thing, add them all up together. And then you could do the same thing for your y variable. And once you find that out, you can find out your R square using this formula over here. So the last part which we want to try and talk about in this chapter is the relationship between the correlation and the coefficient of determination and the standard error of the estimate. So similar to your ANOVA table, the regression equation, the total sum of squares is the sum of the square of the regressor plus the sum of the square of the error. You would notice similarities between the ANOVA table and this table over here. The only difference is instead of calling the sum of square of regression in the ANOVA table in the previous chapter, we call it the sum of squares of treatments. And the other difference being the degrees of freedom are different. The degrees of freedom for both, there it was, I think, k minus 1 and n minus k. Whereas here, we do not have those restrictions in terms of number of treatment groups. We just have like the relationship between two variables. So the degrees of freedom over here is just 1, 2 minus 1. And whenever it comes to single variable regressions, it's 1. And here it's going to be n minus 2, which is pretty much the same as the degrees of freedom from the previous chapter. It's just that since you're comparing the relationship between only two variables, the degrees of freedom tends to be just 1 over here. And instead of writing n minus k, you could write it as n minus 2. This is the same relationship, and you could still find out the mean square values by them. And so the residual error is the sum of squares of error, which is the difference between the actual value and the predicted value. And those values were actually found out over here. These residuals are the difference between the actual value and the predicted value. We found out the actual value and predicted value, and y prime minus y, those are the residuals. And once you find that, you could get the sum of all those squared variables. For regression, it's y prime minus y average, and the total variation is just the difference of the actual value from its mean. And using these values, the relationship is r squared is 1 minus SSE by SST. Okay, and where the standard of error of estimate can also be found out by the square root of the sum of square of errors divided by n of n minus 2. And finding out r squares in actual examples is very, very useful. We look at r squares during research all the time, and we compute regression equations all the time. Regression is a very, very useful tool which researchers, and not even researchers, even in the private practice, the word regressions are used very, very frequently in order to predict variables. Predict the probability of acquisition, predicting the stock price, predicting any value, predicting sales, predicting marketing expenses, and trying to see whether marketing expenses has had an impact on the sale of a particular product. All these sort of things, linear regressions are very important. The difference in terms of certain kinds of softwares is like trying to find out the actual, the t-statistic on, pull it up. This t-statistic over here, and trying to find out how significant the correlation coefficient is. I rarely do it because the software package which I use to compute correlations almost always gives me the t-statistic and the p-value associated with it. I use correlations a lot, but I do not memorize each and every individual formula because these formulas are always available as and when I need them. And remember to try and understand the concept more and when to use it and how to use it and how to interpret these values rather than the actual calculation. For the actual calculations, you could always go and look up the formula and calculate these variables by yourself. In the long run, you should try and understand the interpretation and remember the concepts behind the statistics rather than become a calculation quote-unquote monkey per se, or a regression monkey, they say it in research. And that's it for chapter number 12. And in the next class, we will be looking at multiple regression and how to interpret regressions with multiple variables and the relationship between various variables. Okay, I'll see you all next class. Bye-bye.